All right, moving on to chapter 8.5, we're going to do graphing and writing exponential growth functions. I'm going to try to make this as short as possible, which doesn't mean it's going to be short, but I will do what I can here to minimize it to hopefully no more than 15 minutes. All right, here are the standards. I'm not going to read them. You can read them. If you need to pause it, go ahead. But we're going to go over two of these as we do this, okay? All right, so let's talk about exponential functions. Okay, so um, it is a function in the form of, it looks like this. Y is equal to AB to the x power. Okay, now don't freak out when you see this with all those variables in there. It's just, we're just going to learn how to read it like everything else, okay? Here are the rules about this, though. I'm not allowed to have A equals 0, okay? If A is equal to 0, this whole thing is going to become 0. I get my x-axis, right, where y is equal to 0. So that's the first rule. Second, b needs to be greater than 0. Okay, we're only going to be dealing with positive numbers, mainly because if you use negative numbers, depending on what your exponent is, you're going to get positive and negative values coming in and out of this thing. So to simplify it, we're going to use things that are bigger than 0. And we're going to say that b isn't going to be equal to 1, okay? And because if b is equal to 1, then if I raise it to any power, I'm going to get 1, and then it's really just a line, okay? And we'll explore some, we'll explore what different variations of this look like we'll use some software, we'll use some online activities that are a little bit more, I think, helpful than just trying to graph them all by hand. All right, so these are non-linear, right? They're not lines. So what are they going to look like? And really, when do you encounter exponential functions? So we'll talk about a couple of problems later, but a lot of times what you'll do is we use it to talk about population growth, okay? And by population, it could be anything. It could be a human population. We could be talking about, oftentimes we talk about the population of bacteria. So if you just leave, a jar of water sitting out, and over the course of time, bacteria will end up exploding inside of there, given the right conditions. And the way that they the way that they grow, it follows a pattern, right? And so this is a lot of times where the math is not, we're not coming up with the math and then looking for things that match it. It's sort of, we're using this to describe what we see in real life, okay? So, and they're not going to be perfect, but these are sort of models, okay? All right, so let's take a look. Here's a function, okay, and then here's an input-output table. So I've got x is -2, -1, 0, 1, and 2. That's my domain, my input, and my range, or the output on this, would be y is 2, 4, 6, 8, 16, or 32. All right. Again, what I was saying is, if you have stuff, let's say you're recording numbers, and what we're trying to do here is we're really looking for a pattern. How does this thing change, or how does it move? Is there any kind of, can we predict what the next steps might be based on the numbers that are there? So let's take a look at this. Let's look at how this thing moves, okay? So I want to look to see, is there sort of a regular pattern that happens as I increase x here, right? So I start at -2 and I'm going up to +2. I want to know, as I increase x, what happens to y, okay? So hopefully you can see that and you're looking at this and you're saying, oh, this makes, this looks pretty, it is also rising, right? So let's figure out first, let's see if it's exponential, okay? So as I look at this, okay, as x increases here, right? So here's x and it goes up. As it goes up by 1, okay, I am multiplying by 2. This is doubling, right? 2 to 4, 4 to 8, 8 to 16, 16 to 32. It doubles, okay? Now, if it was linear, it would also increase by adding. So this would go +2 to 4, +2 to 6, to 8 to 10, right? I'd be adding 2. But as I double it, right, as I multiply it, that's the pattern here, okay? And if you think about it, yesterday when you were taking your quiz, or today when you were taking your quiz, I gave you the pattern up on the board and asked you to try to figure out what the next steps will be, and even if you could come up with the equation, okay? And we'll take a look at that tomorrow again as we go through this some more. All right, so what we're looking for is we have y is equal to abx, right? So in this case, b is the base, all right? So remember, we're doing y is equal to ab to the x, okay? This is just going to be some number that I'm multiplying, okay? This is sort of the coefficient. B in this case this is the base. This is the number that's being multiplied, okay? X in this case is the number of times that I am multiplying it, and y is sort of the result, okay? So in this case, when we do this, we're not necessarily, when we change x, it's sort of like saying the step number. As I change the step number, how many times will I multiply? Okay, that's really what the exponent is saying, right? This describes the number of times that I'm multiplying this number, okay? So in this case, what is the thing that I'm doing? Well, as I increase x, right, by 1, I'm multiplying by 2. That means this, as this gets bigger, I continuously multiply by 2. So b in this case will be equal to 2, which is what we're saying here, okay? So I know that I'm taking, right, y is going to be equal to, right, 2 raised to some power, okay? It's going to be raised to some power. And the number x, right, x here, is the number of times that I'm multiplying by 2. All right, so then what we got to do is we got to figure out what is a, okay? So what we're going to do is we're going to find when does x equal 0, okay? And the reason why we're going to do when x is equal to 0, because if I have y is equal to a, right, and I know that b, right, we already figured out that b is 2. Well, if 2 is to the 0 power, right? Okay, so in that last in our function table, we had x was 0 and y was 8. Okay, so I know that this is a pair, right? So I know that when I plug in x for 0, okay, or 0 for x, I know that I'm going to end up with y is equal to 8. Well, what this is going to do is I'm going to say, okay, well, if 2 to the 0 power times something is equal to 8, well, then the nice thing is this becomes 1. So I know that a is equal to 8. So it's sort of like my multiplier, okay? Again, you could also think of this 0 means the starting point. So in this case, this problem, I'm not starting at 1. I'm starting maybe with 8, okay? We could say 8 things. All right, whatever it is. Oftentimes when we talk about this, we talk about bacteria, we talk about maybe cells, we talk about people, we talk about money. These kind of things are usually typically what we talk about. So in this case, let's say you had 8 cells, right, and you know that they double, and I want to know how many I'm going to have after a sequence of doubling, okay? How many times did it double? And I'm sure you talked about this if we've done cell division in science, okay? So again, this is saying a, right? When I'm at the starting point, a, it has to be 8 to give me 8. Okay? Then we'll go ahead and we'll check it. All right? So let's see. Oops. That's what we have right there. Oh, excuse me. Oh. Thank you. All right. So that's my function there. Now let's go back and let's go ahead and let's go back real quick and check it. Okay, so let's take a look. We know that we said y is equal to 8 times 2 to the x. Okay, now if you take these numbers, right, if I take 1 and put it in here, 2 to the first power is 2. 2 times 8 is 16, which then works. Let's try 2. If x is 2, 2 times 2 squared is 4. 4 times 8 is 32. That works. Okay, well, let's try the negative one. So negative 2 to the negative 1 means 1/2. Well, 1/2 of 8 is 4. Good. And then if I did negative 2, that's 1 over 2 squared, or 1/4. What's 1/4 of 8? Well, that is 2. It works. Okay, so that's the idea there. All right, so let's go through these. All right, so this is what I want you to do. I want you to try to come up with the rule for this one. So what I want you to do really is figure out the rule, and then if you really are feeling adventurous, see if you can write it as a function that looks like that. Okay, so go ahead and do that. Okay, hopefully you were looking at this and you said, all right, I noticed that as x increases by 1, right, as x increases by 1, my y values triple, right? They keep multiplying by 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. Okay? And then I know, therefore, it's exponential. Exponential means multiplies, right? It keeps multiplying. If it was adding, it would be linear, because then it would follow a slope. It would have a unit rate. Okay? All right, so see if you can figure out where this, now that we know that B is 3, see if you can figure out what the A value is and if you can come up with the equation. All right, so hopefully you came up with A is equal to 27, since if we go back here, right, the 0 value, when B is 0, meaning this whole thing goes to 1, Y is equal to 27. So that means A has to be 27. Okay, so hopefully you end up with, whoops, hopefully you end up with 27 times 3 to the x power. That's kind of funky. It's kind of hard to read there. So you should have y is equal to 27 times 3 raised to the x power. Okay. All right. So let's talk more about what this thing of exponential growth is. Okay, so when a quantity grows exponentially, it increases by the same percent. Percent meaning multiply. Okay, you're talking about a fraction. Sometimes a fraction is going to be more than 1, sometimes it's going to be less than 1. In this case, with growth, it's got to be greater than 1. So if something is doubling, right, it's the same percent. So that means increasing by, right, or it's increasing by 100% each time. So from 2 to 4, from 4 to 8, from 8 to 16, and on, okay? And over equal time periods, okay? So it still has to, it's basically saying it's multiplying by some amount over equal time periods. Okay, now, you definitely need to write this down. This is what the growth model looks like, okay? And this is what we're going to use a bunch of times. So it's y equals a, okay? But instead of there being a b in here, okay? We had b here before. This is what we're going to talk about, 1 plus r, okay? And that's the thing that's being multiplied over and over again, okay? And then t, and you'll see what that means here in a second. So let's go ahead. And so a is going to be the initial amount, okay? Whatever you start with, it's the beginning part, okay? It's not always going to be 1. Sometimes you're going to start with something bigger. Like in the previous example, we started with 27. That was what it was at the 0 time. So remember, 0 is sort of, again, starting point, and especially when you use 0 for the exponent, that means at the beginning. Okay, r is the rate at which something is growing, okay? Oftentimes we'll use a percent for that, okay? And then once you have that, it's going to give us the base for my exponent, right? And I'll talk about more in class why it's 1 plus r, okay? 1 plus r is the growth factor, okay? Again, that's the thing that's going to sort of give us the base that's going to turn into b in the previous examples. And then finally, t is in the time period, okay? And it's important that we pay attention to the actual units on time, that they are consistent with the things that we are trying to solve, the things that we're looking for. All right, so let's go ahead and let's see. For the sake of time, you know what we're going to do? We're going to solve a problem, and then tomorrow what we'll do is we'll do some graphing of this in class so you get a little bit better idea of what it looks like, okay? So let's take a look at an example of when you might actually see exponential growth. Okay, so let's say a collector car. Say 1953 Hudson, which is in that picture there. A little hard to see, so you might want to Google it to see what it looks like. Hudson Hornet convertible. Sold the car. Let's see. Oh, sorry. The owner of a Hudson convertible sold the car at an auction. The owner bought it in 1984 when its value was $11,000. The value of the car increased at a rate of 6.9% per year. So each year, you'd take 6.9% of the value, add it. Now you have a new value. Then you take another 6.9% the next year, find out that, add it to the value, over and over and over and over again, okay? Well, that gets very tedious to do if you want to do it, especially from 1953 till now. So let's figure out what the value of the car is over time. All right, so let's say the auction took place in 2004, a long time ago. What was the approximate value of the car at the time in the auction? So let's round our answer to the nearest dollar. Okay, so we're going to start plugging this in. We're going to let's say C is the value of the car, and we're going to let T be time in years. Notice in years. Okay, we got to make sure that's true, and make sure that when we do this, it matches with the growth rate, right? Because I think they said in this problem that the growth rate is per year. Okay, so we want to make sure our time units and our rate units actually match up. Okay, so. Finally, we have the initial value, A, right? This how much it started at was $11,000, and we know that the growth rate was 6.9%, so that's going to turn into a decimal of 0.069. All right, so plug this into an equation, and we're going to get exponential growth. So we have the cost is equal to A, right, times 1 plus RT. Right? Instead of having y in that other one, I just substitute c since it's the cost. And we're just going to start plugging in our values. Okay, we've got 11,000. I've got 0.069. Okay, I'm going to simplify that. And then I'm going to substitute in my value for t. Okay, so they said, let's see, 20 years after 1984. All right, that's what we had for t. So we'll plug in that for the exponent. Now, for this chapter, you definitely need a calculator. All right, so make sure you bring a calculator. I do have some in class that you can borrow, but I'm not going to make you do these by hand. That would be cruel and extremely difficult. So make sure you bring it. In this case, you can plug that into the calculator, and you're going to end up with $41,778. Okay, so that would be the final value of the car in 2004. Okay, and that would be an example of exponential growth. All right, I'm going to stop there. This video is long enough. Make sure you bring your notes to class tomorrow, and I will check them in, and we will talk about graphing and how to graph exponential functions.